and I'm from Dayanand Sagar University, Bengaluru. And today I'll be presenting the work we have done, that is multi-mission weave of extra-galactic black hole X-ray binaries, LMC X-1 and LMC X-3. And these are our collaborators. So this is going to be the outline of my talk. Okay, to begin with the introduction to black hole X-ray binaries, this has been already discussed a number of times in past 2 days, so I'm going to skip it and go ahead with the source introduction, that is LMC X-1 and LMC X-3. Okay, now both of these sources are located in the our neighboring galaxy, that is Large Magellanic Cloud, which is at a distance of about 48.1 kiloparsec. And both of these sources are persistent sources, meaning they emit X-ray all the time, that is, it is detectable in X-ray all the time. And LMC X-1 is a high mass X-ray binary, and LMC X-3 is a low mass X-ray binary, meaning the companion star of LMC X-1 is having high mass, whereas that of X-3 is having low mass. And one of the advantage of studying X-ray data from these sources is that it is having very less low galactic hydrogen column density because of its because it's not along the plane of our galaxy. So making use low galactic NH, meaning less absorption of soft X-rays. Therefore, making use of this property, many people have studied the physical parameters of these two sources by, for example, like as you can see here, I have tabulated the previously estimated spin mass and inclination angle. The spin mass is obtained by using X-ray data. That is, the X1 is found to be 0.92, and for X3 it is 0.25. And the mass and inclination are from the optical data, and the values I have quoted here are from these papers. So, okay, in our study, we have used the data from the instruments AstroSat, NICER, and NuSTAR. AstroSat's LaxVC and SXT has observed these two sources quite a few times in between over a period of 2016 to 2020. Here I have tabulated the number of observation of X1 and X3 by these three instruments. So that we have obtained all available public data from all three instruments. And AstroSat's data includes the archival public data along with the legacy observation, which was done in 2020. It's a recent observation. And yeah, so where exactly these observations are, when exactly these observations are done is I've marked all the observations here. This is the maxi plot for the light curve for the period of 2016 to 2020 in the energy band 2 to 4 keV and 4 to 10 keV. And in the bottom panel, I have plotted the hardness. So I have marked AstroSat observation that we have considered in this study in black lines, and NICER in red, and NuSTAR in blue. And the one more thing we can see in this notice from this light curve is that LMC X1 is showing very less variability, whereas LMC X3, when compared to X1, is showing very high variability. We see that later that this is associated with a change in the spectral state. Coming to data reduction and analysis. So we have used the standard pipeline softwares and reduction procedure. That is, we use LaxVC SAW for AstroSat data, and NICER does for NICER, and NuSTAR does for NuSTAR data to obtain the spectrum and light curve. No, okay, here I show the SXT and NuSTAR image of LMC X1 and X3. That is, the one on the left is X1 and the one on the right is X3. And I've also marked the circular region of radius 10 arcminute from the region from which we extracted the spectrum and light curve. Okay, coming to spectral results of LMC X1. Once we obtain the spectral data, we modeled it using the model combination TBAPS, DISPB, and power law. Okay, as I've already said, the galactic NH for these sources is really less. So what Hanke et al. 2010 have done is they have considered the elemental abundance of the host galaxy, that is Large Magellanic Cloud, and they have found the hydrogen column density along the line of sight of LMC X1 to be 1.3 into 10 to the power of 22 per centimeter square. And we did the same thing. We took the values of elemental abundance in LMC and we adopted in our TBABs, and we obtained the same value, that is 1.3. And we have used this value for all the analysis of LMC X-1. And once the spectral fitting was done, we found that all the observation from all three instruments were extremely soft. This is expected because LMC X-1 is known to be persistently in soft state for very long time, and we confirm that by using the recent data. And in the plot that I've shown here, I've plotted the spectral best fit for different epochs, and as you can see, there is no much in it. All the spectrum of different epochs are pretty much exactly the same, and yeah, so there is no particular significant change in the flux. Coming to spectral results of LMC X-3, we modeled the energy spectra using same model combination, that is this PB and power law along with TBABs, and we have adopted the elemental abundance of LMC as well. And initially when we modeled the AstroSat data, we found that all the observations were in soft state. However, when we modeled the nicer data, we found that for a brief period of time, around at the end of 2018, the source transited into intermediate state and to hard state only in one observation, and back to intermediate and soft state. And this has been seen in by using nicer data. And we classify this into intermediate state and hard state solely based on the spectral index value and the contribution, that is contribution of the disk flux to the total flux. That is, in soft state, we found the disk contribution greater than 85%, and in intermediate state, it was in between 50 to 75%, and in hard state, it was very less, about 26%. And from the spectrum that I've plotted here, you can see the clear difference between the soft state and hard state spectrum. That is, the AstroSat 1, which is green and red, are plotted for soft state, and the blue, which is nicer observation, that is hard state observation. We can clearly distinguish between these two states here. Okay, since we had a large number of soft state observations available, we tried to constrain the physical parameters using the model Simple and Kerr-BB, and we adapted the known values of distance and inclination angle, and from this spectral fit, the spin of LMC X-1 from AstroSat data was found to be in between 0.82 to 0.92, and from NICER 0.88 to 0.92, and the rest of the values, as you can see here in the table. And this is consistent with the previous studies which I have showed in the first in the introduction slide. And this result that we have obtained from the AstroSat data alone has been submitted to MNRS, and which has been accepted for publication. And the one with NICER and NewStar is under preparation. Okay, this is the contour plot of spin versus.
You have 2 minutes, huh, Bhuvana? You have 2 minutes left.
Okay, yeah. This is the plot of spin and mass, spin versus mass, plotted using MCMC, and the left one is that of LMC X-1, and the right one is that of LMC X-3. And you can, from this plot, you can see the range of values of spin and mass of both the sources. And in the timing, and when we did the temporal analysis, we did not find much from this. Like, we did not find any QPOs from any of the observation, even though millihertz QPOs has been detected in LMC X-1 in the soft state before by using from other data, but we did not find any in our observations. And even for LMC X-3 in the hard state, we did not find any QPOs. But we did calculate the fractional RMS for the frequency range of 2 millihertz to 10 hertz, and we found that during soft state the RMS is less, and in the hard state it's comparatively high for LMC X-3, and this is as expected. And we also saw that the short-term variation of LMC X-1 is higher relative to that of LMC X-3. As I showed in the maxi light curve, long-term variability is higher for X3 and lower for X1, but the short-term variability is higher in case of X1, and this has been explained. This could be due to LMC X1 is a high mass X-ray binary and the mass accretion is taking place via stellar wind, and LMC X3 is a low mass X-ray binary. So mass accretion is taking place via Roche lobe, and so there will be a steady inflow of matter. So there is no much variation in the short time scale.
So Bhuvana, you have finished your time. Can you end soon?
Yeah, sure.
Okay.
So sure, this is the summary which it contains all the points that I've already discussed. So I would like to thank ISRO